It's usually pretty helpful to see a bunch of problems done, in this case using anti-differentiation and substitution. I'm also going to hopefully get you to see when this technique, substitution, should and should not be used. If you watched the last video, this might be pretty obvious that we should use substitution. We're still showing the substitution, although eventually, hopefully you can do these substitutions in your head, just like there have been earlier things in the year that used to be hard and now are easy. Let's rewrite cotangent as cosine over sine. And when we're doing substitution, we want to have du, I guess, in the numerator. I don't know, how do I say that? Well, we're looking for something that has a derivative somewhere else. And in this case, that's sine of x. Let's work ahead and then tell you why in a moment. Du is cosine x dx, and that's actually what we were given up top. Cosine of x is being multiplied by dx. That's the only substitution we can make in order to get a du. So let's rewrite this as cosine of x and dx become du, and sine of x becomes u. Or you can think of that as 1 over u times du inside the integral. What has the derivative 1 over u? Natural log. We need absolute value because u might be negative, and in fact, u is sine of x. Sine of x is negative a lot. Can you see the substitution here? Well, you might think you can. I'm guessing at first glance you might not. I'm going to need a lot of room to work here. So what doesn't work is u is equal to x squared, or even x squared plus 4, because then du is 2x dx. So you can't put a 2x up top and a 1 over 2x. Heck, that's outside the integral. You can't put a 2x down here, because then, let's see, what does that mean? That means 2x and dx would become du. We would end up with 2x times u. Now, number one, we want u's and du's only. And number two, when you divide it by 2x, that actually creates a quotient rule sort of problem that you didn't have earlier. You should only be dividing by constants. All right, well, if that's not the u, well, maybe there was something else. Is this some derivative you know? It actually, hopefully, is. You should be thinking, that's me thinking, the derivative of inverse tangent is 1 over 1 plus the input squared. So we're close to that, except for that little 4. So let's think. How can we turn a 4 into a 1? We're going to multiply by 1/4 in the denominator, 1/4 in the numerator, and do some algebra. 1/4 in the numerator, I'm going to bring out front of the integral. We'll still have 1 in the numerator of the integrand. And x squared times 1/4 can become x over 2 quantity squared. Hopefully that works out for you. You might think x squared over 4. Well, this x over 2 quantity squared is x squared over 4. And so now, hopefully you can see that u is x halves, which means du is 1/2 dx. Well, we have a dx. We need a 1/2, which we have part of out here in terms of the 1/4. Let's rewrite that 1/4 as 1/2 and leave our, maybe we can just substitute this right now. X over 2 becomes u, and 1/2 dx is still left over here. This 1/2 multiplied by this 1/2 is this 1/4. Okay, so 1/2 dx can now become du. 1/2 the indefinite integral 1 over u squared plus 1 du. Let's start a new line of work. 1/2 the antiderivative of 1 over an input squared plus 1 is inverse tangent of that input. Don't forget your constant, and let's go ahead and resubstitute. Inverse tangent of x halves. Okay, evaluate, show the substitution. Well, I think, hopefully you're thinking u is not cosine squared 2x, because then du would be 2 cosine of 2x times negative sine still of 2x, chain rule again times 2. And I'm not going to be able to get any of that stuff. Well, could u be cosine of 2x? Then du would be negative sine of 2x multiplied by 2. Maybe. Let's make one substitution, and if we just substituted right now for one of the cosine of 2x's, we'd have u times cosine of 2x left over. Oh, forgot my dx. And I don't think we can change cosine of 2x in the denominator into any version of sine of 2x in the numerator. That didn't work. Well, maybe this isn't a substitution problem. What else do we know about cosine? Well, it's the reciprocal function for secant. Oh, that wasn't the substitution I was thinking. The substitution is simply 2x. Okay, and good practices, instead of dividing to find dx, we're going to multiply to make this 2 dx. So we'll multiply dx by 2. We'll multiply the whole integral by 1/2. 2 times 1/2 is 1. And now we can substitute. Secant squared of u and 2 dx becomes du. The antiderivative of secant squared is tangent, and all we have to do is get back to x as we started with, so u becomes 2x. All right, is this inverse tangent? It is not. I can see the derivative of something represented somewhere else. Do you need a hint? Later on, I'm going to put a 2 next to that x. So my u is going to be x squared plus 1, which makes du 2x dx. I saw ahead I wanted a 2x dx, so I put a 1/2 out front. So what do we have now? 1/2 the indefinite integral, 2x dx become du. And we end up with 1 over x squared plus 1 becomes 1 over u. You might be thinking, hey, can we just go from, maybe I'll write it. Can we just go from 1/2 the indefinite integral of 1 over u du to 1/2 natural log of the absolute value of x squared plus 1 plus our constant? Yes and no. In the real world, sure. Your job on the AP test is to show what you know. The antiderivative of 1 over u involves a u, so we'll show that, and then we'll show the resubstitution to make sure we can get all possible points. Ooh. What the heck can we do here? Do we know anything that has the derivative cotangent squared? We can have secant squared, cosine, no? So what is this? maybe we can rewrite this as, oh, I know what to do. Ha ha ha. Takes me a second. Well, let me show you what not to do. You might think because we had this earlier, we should write cosine squared of 3x over sine squared of 3x dx. Can you figure out why this won't work? Well, you might be thinking du could be cosine of 3x dx, which would make u sine of 3x. I guess we'd end up with an extra 3 here for that chain rule. But we haven't dealt with the squareds yet. Okay. Well, maybe u is sine squared. That would make du2 sine of 3x, chain rule, cosine of 3x, chain rule times 3. I don't know, but I don't think I can make 2 sine cosine of 3x into cosine squared of 3x. So what you're going to have to use, what I'm going to use, is a Pythagorean identity. Sine squared plus cosine squared is 1. And so I want to get cotangent. I'm going to divide everything by by sine. Sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent squared. And 1 divided by sine squared is cosecant squared. Ideally, you'd be doing this in your head, but that's pretty hard to follow. Okay, so cotangent squared is going to be cosecant squared minus 1. So the indefinite integral of cosecant squared of 3x minus 1 dx. And now it's very obvious to me that u is just 3x. Because we know the antiderivative of 1 with respect to x is x. And cosecant squared is the derivative of cotangent, although we're missing a negative. Okay. So the indefinite integral, oh, we need a 3. Let's go back. Let's put a 3 in, squeeze a 3 in right there, 3 times dx, so we'll divide by 1/3. 1/3, the indefinite integral of cosecant of u, or cosecant squared u, minus 1 du. Let's do some antiderivatives. What has the derivative of cosecant squared? Cotangent, except the derivative of cotangent is negative cosecant squared. What has the derivative 1? That would be, in this case, u. I just distributed the 1/3 so I wouldn't forget later. So 1/3 cotangent, cosine, of 3x minus 1/3 of 3x plus our constant. Ooh, this one's tricky. Very related to the last substitution. So, when you see cosine, hopefully you're thinking a derivative of sine, but turns out u is equal to sine of x, and du is equal to cosine of x. Which means, I guess, when we do a substitution, we'll end up with cosine squared x times cosine of x dx is going to turn into although I don't have any u's, so what the heck am I talking about? Show you what I'm talking about. This works whenever you have odd powers of sine or odd powers of cosine that you need to integrate. So we're going to say cosine squared x and cosine of x dx. You already saw this cosine of x dx is going to be du. So that means we need to find a sine somewhere in cosine squared, and that's that Pythagorean identity again. I'm doing this in my head, so here's me, here's my head. Sine squared plus cosine squared is 1. And so cosine squared is 1 minus sine squared. So hopefully now you can see that we can say u is sine of x, which makes du cosine of x dx, and we can make our substitution. 1 minus u squared times du has the antiderivative u minus a third u cubed plus a constant. Resubstitute sine of x minus 1/3 sine cubed plus a constant. I don't know, does that work out? That seems a little bit complicated. Maybe we'll do a derivative to check. So y equals sine x minus 1/3 sine cubed plus our constant. Let's make sure y prime is cosine cubed. We'll probably have to do some moving things around. The derivative of sine is cosine. Let me get a little more room. The derivative of sine is cosine, and let's see. The derivative of something cubed is 3 times that something squared. Sine of x is the input, so cosine of x on the chain rule plus 0. So let's see, what do we have? Y prime is cosine of x minus sine squared x cosine x. That doesn't look like the cosine cubed we started with. But we can factor out a cosine and be left with 1 minus sine squared, which 1 minus sine squared up top, that's cosine, so y prime is cosine of x times cosine squared. Hey, that does work. I feel like I've done this before. Ooh, 2 ways to do this substitution. Secant squared x tangent x. What are your 2 options? Ooh, how fun. Let's do both. So we want our derivative to be somewhere else. So the tangent pops out at me first. Du is secant squared x dx. And that's good to go. Tangent of x. And everything else is our du. What's the other version? U could be secant of x, which would make du secant x tangent x. Those are going to both work out. You're going to get something slightly different, but everything is made up by the end and is explained in terms of that plus a constant. I'll let you finish that one if you want. What would you do here? Well, we would do the technique I showed you before. Since this is sine to the 5th power, we're going to break off one of those signs, and that's going to be du. And so if du is sine of x, I'm trying to work backwards to show you what I'm thinking. U must have been, actually, I guess negative cosine of x. Maybe this is positive and that's negative. Doesn't matter. Which means somehow I need to turn sines into cosines. And it's that Pythagorean identity again. Sine squared plus cosine squared is 1. We just end up doing that thing twice. So let's do the work in order. Hopefully that's a little bit of a hint as to where we're going. Think of this as sine squared sine times dx, which means we can rewrite sine squared as 1 minus cosine squared. This other sine squared is a 1 minus cosine squared. And we'll leave this sine x dx at the end. So u is cosine of x. du is negative sine of x dx. Let's toss a negative in here and a negative out front. We'll have negative 1 minus u squared times another 1 minus u squared times a du. I'm not going to finish everything, but I'll give you a hint. 1 minus 2u squared plus u to the 4th, I think you can finish from there. Ooh, a little bit tricky. What should we do here? Well, I'm not sure, but that cosine cubed, that feels like I should change things into sine. Let's go ahead and try that. So let's rewrite this as 1 minus sine squared, leave a cosine of x, over the square root sine of x. So what can we do here? Let's see what happens if u is sine of x. So that would be the indefinite integral 1 minus u squared over the square root of u and then du. Well, that looks cleaner. Can we do the derivative of all of that? Should we substitute again? No. It's just powers. The indefinite integral of u to the power negative 1/2 minus u to the power 3/2 du.